Okay, we're going to work on this problem together. This is a problem that utilizes the quadratic structure, even though we're dealing with higher degree expressions here. So as you can see, which expressions are equivalent to this x to the fourth plus 3x squared plus 2? And then we have four pretty unique choices here that we need to kind of see if any of these are candidates. The first tactic I'm going to use is to rely on a factoring structure we've known for quite a while. So what if we just viewed this as a certain value squared plus 3 times a value plus 2? And what I'm getting at, might be a little bit nebulous at first, is a structure. In other words, in Algebra 1 when they're teaching factoring with quadratics, we just have x in there. So let's just start with that. We have x squared plus 3x plus 2. This is a trinomial, it's 3 terms. And whenever, it's a real nice case whenever we have 1 on that leading coefficient. We can build x squared by just going x times x. The real puzzle to figure out is what are the constants in those binomials. And so the way you figure that out is you look for factors, things that multiply to 2, that add up to 3, the b value in this case. All right. And so 2, it's prime, so we don't have a lot of factors to go through. It's going to be 1 times 2. And in order to get a positive 2, they either have to both be negative or both be positive. Since your b value here is positive, we're going to go plus 1 and plus 2. And you can certainly see how that would multiply out to be x squared plus 2x plus 1x plus 2. And there's your bx term of 3x, okay? So if we kind of piggyback on this quadratic structure and view this fourth degree as stuff squared plus 3 times stuff plus 2, okay? And inside, instead of just having x, our inner structure is x squared. All right, this is pretty cool because what we could do is utilize that thing we were comfortable with, and instead of having just x plus 1 and x plus 2, it's actually x squared plus 1 and x squared plus 2. So that's kind of a leap for people right at first to realize, oh, if I have an even powered first term, my highest degree term is even powered, and then that middle term in the trinomial is exactly half the power, then I can use this, possibly use this kind of a factor pattern. You just have to be able to look for factors of that constant that add up to the appropriate b value. Okay, so the good news here is once we've applied that factoring technique, we can see that this is answer C. If you apply the commutative property, I know the order of multiplication is different there, but that is answer C, just in a different order. Okay, so as we look at the others, they look quite a bit more involved, and you might just flinch and say, hey, I don't think any of these work. But what we want to do is kind of pick out some things that we notice here. So what I notice is that compared to this answer in C, I have up here in answer A one of the same factors. And so what that kind of leads my eye to wonder is, I wonder if x squared plus 1, one of those factors we just found, is going to break apart into x plus 1 times x minus I. And you could check that two different ways. Okay, you can quickly just do the distributive property here and see if you get that little guy, x squared plus 1. Or you can try to apply that technique we have lately seen using the identity for I squared equals to -1 and the difference of squares. It takes a little more effort, but it's beautiful in my opinion. So that's x squared, double negative instead of plus, we insert a double negative, and then 1 squared is certainly 1. Okay, then we take this phantom -1 here, and we substitute in an I squared. So we've got I squared times 1 squared. The front of this quantity x squared there is just going to stay put for now. And then we could pull, since these are both being multiplied and they're both raised to a power of 2, we can unify that quantity and say I times 1 or 1 times I is how I like to write that. And they're both squared. So now I've got this difference of squares factor pattern that I can now kind of pop apart with that conjugate look we've seen time and again. And so that'll be x and I. So one I, and one of them's got to be negative and one of them's got to be positive. So this is utilizing that difference of squares factor pattern that we had notes on the other day. Okay, but if you if you want to, you could have confirmed this by just multiplying these two factors out up here to see if you do get this x squared plus 1. So we've shown it either way. And so A is another candidate for equality with this original expression. Interesting. Now go back to what we just did here, and let's write it out, okay? Or I guess it's already written out. So let's look at what that's given us. Okay, so if we have x squared plus 2 times x plus I times x minus I see that x plus I and x minus I down here, and then on D, it appears that they're exchanging out the x squared plus 2 for this x plus I root 2, x minus I root 2. Okay, so you may see that or you may not. And again, you might have to tackle this from just going at these with brute force and distributing them out to see if you get back to here. All right, so I'm going to try to, in an effort to check D here, I'm going to try to factor that x squared plus 2 to see if it does break down to that, because I already know I can get this other part. We already did that just a second ago. So x squared plus 2, let's break this into a double negative in exchange for that addition. We know it is x quantity squared. And instead of 2, I'm going to have to rewrite that as radical 2 squared. If we're trying to use the difference of squares, we have to do it that way. Okay, now I go after that negative phantom 1 closest to it, and I substitute in I squared. All right. And we are trying to get this last term here with the I unified under that one layer of squared operation. And so we've done that. So I squared times root 2 squared. Just pull that I into the root 2 layer there multiplicatively and have that collectively squared. So now I could rewrite this as a difference of squares factor pattern. X minus I root 2 times x plus I root 2. Okay, so we've done it. We've done it. And I know it's in different order again, but again, multiplication, we can commute the order. So we've confirmed that D is another way of writing this out. And so it leaves us with B. And B is a weird one. Okay. I have this oopsies. Where did my little pen go? Oh well. Is it this? There it is. So trying to confirm that B gets us back to the beginning at all. The problem I have with this is it's got this little term at the end. There's really, and none of these other factors, I should say, look like what I've got along the way so far. So I'm really pretty leery and skeptical of this one. But here's what we're going to do. Let's take B, and this is kind of my last tool I like to use, but we can brute force multiply this out with the distributive property and do some simplification. to see if we actually can combine like terms and get back to where we started. So I'm going to get into this here with the distributive property. X squared times x squared gives me x to the fourth. X squared times negative 1 is negative x squared I. And then we've got another product here. 2i times x squared gives me positive 2 x squared I. And 2i times negative I is going to be negative 2i squared. So as you combine those, you're going to have x to the fourth positive. So these are wonky mixed numbers, I get it, but this is a negative 1 and this is a positive 2. So that's positive 1x squared I. And then don't forget your I squared here is negative 1 if you're simplifying like we are now. So you're going to end up with a plus 2 from that term. And then don't forget to bring down that separate term that had nothing to do with our distribution, but now it's possibly a like term. In fact, it is. I could see it right here. It's opposite of that. So it's funny how that kind of comes back to be the opposite and cancel out that value. So we do get down to something much more beautiful than I thought it was going to be. But folks, it is not what we originally wanted. So I have to put a little frowny face here and say bad news bears, B is not a candidate for this equality. So A, C, and D is it. Good luck.